All right, so today we're going to start about the basic definitions and synthesis examples for our coupling matrix. This is the tool that we have been building over the last few lectures. And I'm going to basically start by showing you a more complete diagram of how the coupling matrix looks like for a typical filter and the symbols and what they mean. We will also learn finally to synthesize the filter response based on the numbers and the symbols you will see here. So as we have seen before, a typical bandpass filter or any other filter actually will consist of a series of resonators shown with this blue color here. Those resonators will be coupled to each other through the inverters, and the inverters are actually shown here with these coupling coefficients M, so they're not explicitly shown with the little boxes that you saw before. But in addition to the direct coupling sections that I just highlighted, there's also the possibility of the cross-coupling sections. So for example, this here is a cross-coupling section, and this here is a cross-coupling section. So in theory, there is a need for many filter responses to have multiple of these cross-coupling sections. But it's also important to realize that even if you don't intend to have a coupling section, parasitics may introduce one. So a lot of times, people who actually lack this knowledge try to understand why, for example, an extra transmission zero or an extra pole exists. And when you see something like this, it's almost certainly a parasitic coupling that you can actually introduce and get rid of it. We also are going to assume that we have real loads, so a real load here and a real source here, and the rest of the things we've actually talked about before. All right, so this is essentially a little bit of a reminder of what the symbols mean, but there's also some new information that is used quite commonly in the filter literature. So we use the terms synchronously and asynchronously tuned filters to essentially signify whether we're tuning all resonators at the same time. So that means that when you have a synchronously tuned filter, your resonators are all at exactly the same frequency, or whether you have resonators at different frequencies, that's the asynchronously tuned filter. Both are possible. They both have pros and cons. By far, the most common approach in the literature is to have synchronously tuned filters because that's essentially the easiest one. But the asynchronously tuned gives you a few advantages. For example, you can actually detune resonators from each other to compensate for fabrication issues. So if you have, for example, tolerances that you have to meet, it's possible to slightly tune resonators at different frequencies and actually cover for them. Also, as you're looking at the coupling coefficients, these M's, we have already seen coupling coefficients between resonators. Before we have called them, for example, K and J, and because they're the same, we're going to be using the term M. But in the coupling matrix, there is also this self-coupling that we have seen before, the M11, for example, or the M22. And a lot of times people are thinking of what does this mean. So in a typical scenario where you have a synchronously tuned filter, those self-coupling coefficients will actually be 0. So the M11 will be 0, the M22 will be 0, the M33 and so on will be 0. That's the case for a synchronously tuned filter. However, if you see a coupling matrix and those coefficients are non-zero, it basically means that you have now an offset from the resonant frequency, and that's basically the physical meaning of the self-coupling coefficient. So basically putting everything together, a typical coupling matrix looks like the one that you see right here. And I do want to mention that in theory, this is a reciprocal network. So really only half of this coupling matrix is useful. The other half is just a copy of it. Also, it's important to realize that these coupling elements are in theory complex numbers. So in general, you should expect to see coupling matrices with complex numbers for real filters, even though everything we've seen so far is basically real numbers. Now let's talk a little bit about the pros and cons, which we have kind of covered in discussion sections before, but I wanted to kind of put everything together here for you so you have it together as the most important pros and cons of synthesizing coupling matrices, filters based on the coupling matrix approach. So the first thing that I would like to mention is that the coupling matrix is truly a full representation of the network. That basically means that by looking at this table here, by looking at this matrix here, you know pretty much everything about the network. there is nothing that you don't know. You know, for example, if your resonators are synchronously tuned, you know how many couplings exist, what couplings they don't exist. And as we'll shortly see, by using very simple equations, you can directly go from here to calculating the S21 and the S11 of the filters, the S parameters. The second part that this one gives you is that it actually teaches you the coupling topology of the filter. So by knowing, for example, that maybe the M02 is non-zero, that means that you have a direct coupling between the source, and maybe here is resonator 1, here is resonator 2. Now you know that there is kind of coupling between the source and resonator 2, for example. So it actually tells you in a very physically intuitive way, physically meaningful way, what is the topology of this filter. As I already mentioned, it gives you a very easy computation of S21 and S11. We'll see that in a minute. The other huge advantage of this technique is that it doesn't work just for lossless scenarios, which, as we know, they don't exist in real life. They exist approximately. But if you want to actually find out what is the S21, including the Q of the resonator, then there is a very simple way to do that, and that's something we will also see before. And perhaps the most important advantage is this last one, is that it's a very popular tool. The literature actually has hundreds of papers talking about this, so at least you have a good starting point for the problem that you want to solve. That's not true, for example, if you're going to go for an analytical technique or a numerical optimization for any given topology. Now, the most important drawback, also listed here, is that it is a narrowband approximation. So when you see a matrix, for example, here, and you have to hit a coupling section of 0.52, it basically means you'll hit that at only one frequency because your inverters will change. And so you need to be very careful that the coupling matrix will give you a good response close to resonance, so you will get something like this, but away from resonance, it's likely you will see things that the coupling matrix will not predict for you. All right, so these are the equations I promised you. So here's basically the S21 and S11. If you know the coupling matrix. The coupling matrix here is shown by this M. So this is the one that we just saw. And you need two additional matrices, basically the matrix R, which is shown right here, and the matrix U, which is shown right here. So matrix R is very simple. It's basically zero matrix except for the very last and the very first elements. And similarly, matrix U has only the main diagonal with the elements that you see right here. I have color-coded some of these elements so you can basically understand whether they represent something related to the source, the load, or the resonators. Now, the losses scenario is something we will discuss a little bit later, but I do want to say that it's a very simple modification of either the R matrix or the M matrix itself to actually include losses. So simply by changing a few numbers, we'll see later on, you can immediately incorporate the lossy resonator. In other words, you can immediately incorporate a finite Q here that you can't do normally. And finally, so far at least, we have seen coupling matrices that corresponds to the normalized domain. That means to the domain where omega is equal to 1. So you should remember that once you have these responses, so the S21 shown here and the S11 shown here, you do have to transform to make a frequency transformation, a frequency mapping, essentially to get the true response that you want.